Okay, I'm recording. Proceed. Just give me some time. We will start our class soon. Okay. Um, I feel like I'm not really able to talk anymore. But I'm trying. Um, I'll try my best. um, Slightly recap. First thing because my previous lab I extend my assignment to Friday night. So I don't know, some of you are working it because I'm not yet upload my the video. Actually, if the video is already have some solution, you're able to, if you pause somewhere, you will see all the solution, your answer. Okay, but I will wait until the last, maybe tonight I'll upload it, so you have, if you really not able to finish it, you can refer to the, like, my recordings and then stop somewhere, then you may be able to see it. Okay, but so far, do you have a problem working on the assignment, or could you like figure out the logic? Yes, so far it's okay. So good, yeah. Because as what I say, because for learning operating system, C purpose is kind of like good language, because we are like kind of like low level language. We are really we can touch the like memory, but mainly we try to simulate how the operating system manage the process, like using the register program counter. So always thinking using, try to write a program to simulate like what we're talking, like different stage, to like fetch a cycle, put the things to memory. If you able to pick up the logic in this way, then it may be easier. But I know it's tough to follow my source code. Sometimes like, it's not like implement by yourself, so it's hard to follow the logic. So it's okay, I can go through it with the logic of that one. And last time we talked about multi-threading. So that one is like, okay, one is called the different approach, and one we call the kernel. That means that, okay, if I don't care about the kernel, but we have like benefits or disadvantage, and just need to know about this one. Okay, if I don't know the kernel, it doesn't do the multi-threading, that means like, okay, for the application layer, the process, yes, we can handle it, but we still like waiting for the line and then let the kernel to deal with it. Okay, so this is the only like disadvantage of it. And last time I upload, I only execute only one file. Oh, I close my D2F. Sure. Okay, and let me do it one more time. Okay. So, okay. Yes, sleeping mode. Come on, wake up. Okay. Okay, you are able to see. After you submit the assignment to, so actually I will give you enough time to work on the next assignment. If you still remember, there's a 1 day in the lab. Let me enlarge it. So we try to think about writing a pseudocode. As I let's say I have one resources and then I have two processes. How can I manage it well, like using the while, using loop, like doing some stage to check it, right? So that one is a pseudocode. And coming assignment, we will like simulate. Okay, so how can we do that? You can refer to the three files. Actually three, but total will be six because all of them I will like try to import. I say request another one is for the child, for the worker. But because when we do the fork is a system call. So system call is like kind of like create exactly same copy of it. And so all of them they have their own like PID. All the PID, and then when we import, they will execute their own functions. So let's say in here, if you look at the week 6 2 right here. So let's say I have a number of processes 3 and then the resources 0 is like what is sharing. So right here is the example. Is like I'm going to update the value and make sure, okay, how many processes. And when I execute the worker is right here. If you want, you also can download all the files because I think some of you already have Node.js, then you can execute this JS file and see how it worked. Okay, so when it work, when we import, then we will call the function. So you see the process on. So what this process on is doing? Okay, so we are log function. So we need to make sure like when we share, like it's a global value log. So we make sure like we still have a for loop, like we will execute 5 times. So 5 times, okay, I make sure if I executing this one and I make the log is like true. This one just simulating, but later we need to pass it as a global. So we need to let all the child process like only share is like we call a flag. So if we remember the pseudocode, like we try to make sure that one. So when you implement the like using the cpurpose file, then make sure okay, we have one global is a flag, and then to access it. So all this we have the ID, and then we will execute like 5 times from 0 to 4, and then the I like from 0 to 4, and then when it's not locked, then I will set it to true. That means it's like because we have 3 processes and then the loop at like 5 times, right? So we are trying to make sure when this process get the like grant the right to update the value, then I just make sure okay, I have the right, and then change to true. Then when other process like if I let's say P1 get the access, then I will make sure P2 and P3 they will read the value of log, right? So this is true. That means I'm not able to execute. So here is the code right here. So I will make sure okay, it's not allow them not able to execute. And then when it finish, I will just like make it to false. So once I make the update the value, so it will send it back. So we see right here, when we return the value, so it goes back and add the resources. Okay. Once we finish it, and then we will set it as like release, send it release, then we set the log like false again, and we release it as false. So that means other process are able to update the resource, this variable. Okay, that's how it works. And here's the idea, like using the flag and also like updating when the access. So how it works. Actually we will based on this one. So this one is the JS file is like is the demonstration, as I say in from the last class, to letting you know, okay, this is right. But you need to rewrite in a C+ file. Okay, that's all good. Then we will move on to the today's lecture. Right here, 5. Okay. So for we talking the operating system, we have like the internal and also what's the design principle. So just like our routine controlling the concurrent activities. So we have because we're multiple process. So we can before we talk about history of like unit programming, like just like when we loading the file like one for the action, we only can handle one process. We need to really wait until that process complete, then we can move to the next one. But nowadays, like we say the modern computer, we always say that we do the multitasking on the multi-thread thing. That's like how it works. So it's how important to do that. So the operation is that concerns the management of the process and the threads. So with multi-programming, multi-processing, and distributed process. Here's the key concept. We talk the concurrency, like I raised the 3 different contexts. So we have multiple applications. So this multiple application, we sometimes we call it kind of multiple programming. So we develop like to allow the switching between the multiple running programs. So how can we switch it? And also like structured application. So some of the application, like we say, naturally designed as a set of concurrent process. For concurrent process, we can take an example. Maybe we have a printing job and waiting, so they can like execute in the same time. Okay, and also the even itself, the operating system itself also we need to like it will execute lots of service running in behind monitoring. So actually, OS itself also is a program. So that's why, like, I think before you asked the question why, like, the PC is not always start from 0, because when you click on the button for the BIOS load it, the OS is already occupied the memory. It's like it holds part of your main memory. For here, like for the concurrency, like atomic operation, so the functions or action implement as a sequence. So most of them is like sequence. And all those like maybe one or more instruction that appears like in the visible, and there's no and other process that can see and the intermediate stage or interrupt the operation. And we have also some like called a critical section. So the section of code within the process that require access to share the resources. Okay, so when we simulate, we say share resources will be that one. And then there must be not be executed like while other process is in the corresponding section of the code. So here's the reason why like we like using the JS code to simulate why we need to create a flag. So it's how we simulate the it's a critical section. And also you this one we talk about the deadlock. So I remember in my the third example V6.3. So that one is like try to prevent the deadlock. So it's like in case we have 2 or more processes are unable to process because like each are waiting for one and other one's to do something. That means sometimes the 2 application we always have 3 or it's possible multiple process. They okay, maybe I'm waiting for your return and then I'm waiting for another one, and then some that they're not releasing, some are not able to grant it. So we get into a deadlock. So it's like circle, say, I'm waiting for you, you're waiting for me. So it's like we're never able to execute. Then how can we prevent this type of like situation happen? So it'll be deadlock. So I would leave sometime look at the number 3 and try to execute and look at it. And we have that called the live log. So it's like just in the opposite like website. So it's like more process continues like changing their state in response, changing others process without doing any useful work. Just like keep changing each others. So how can we try to prevent it? Also the mutual exclusion. So the requirements that one process that in the critical section. So critical is like need to waiting the share process like need this And then the SS the shared resources, and no other process may be in the critical section that access any of these shared resources. Okay, it's a long thing. And also we have the race condition and a situation like we have multiple threads, the process like read and write a shared data item, and finally reset depends on relative timing of their execution. That's why reason we need to set the flag, like to preventing, okay, if process one is writing the file, maybe others like need to retrieve it. So how which version of which time slot like rely on? Most of the time it happens like, let's say I have a calculation on math, maybe the origin, I say the register, let's say register A, origin value is 10, and then P1 will up like maybe plus 10, and P2 minus 10, and then P3 will be like divided by 10 like this. But if let's suppose the one like which one maybe P1 associate, then suppose that if I'm running in this sequence, it's okay. Then maybe I will minus and add it and divide it. But if I like original value is 10 and then I execute minus 10 and then division first, then because 0 divided by like maybe we cause the error like this, and then you cannot execute plus 10. Okay, so we need to know. So this one is called the race condition. And the starvation, and then this is a situation where the vulnerable process like overlooked indefinitely by the scheduler, although it's like able to process, but it never chosen. So sometimes this one the scheduler we still have a pretty long PowerPoint to go. So we will learn one thing called a scheduling, because why not still more like conceptual things like theory, keywords like vocabulary. When we have multiple processes need to execute, then we should have some like mechanism doing scheduling way. One thing is like time-based. Okay, let's say like every process have 1 second to execute. So once it finished, I'll go to the next one. But it's possible the scheduler like just overlook and miss this one. So it didn't execute. So it's going to, and then what is the principle of the like concurrency? So we just need to know here, including the risk condition of the mutual exclusion. Right here, like interlifting or overlifting. Okay, so overlapping, so we can view as example of concurrence process. So they will like present the same problems. Okay. In the past, we have the unit processor, so the relative speed of execution process like cannot be predicted. So because we have only one, so unit process every time only one instruction goes in. So really like depends on different other like process, also the way of OS handle the interrupt or schedule policy of the OS. That's how we know, because when we have first like, because when the the CPU try to execute the instruction of that process, because when we running as a block of block, but we never know how like actually how big is it or like how long is it, so we never know when you're going to finish. Is the things. Also sometimes maybe that process will be requesting multiple interrupt input, so that's why we never know. Also when we doing this, also the difficulties mainly is that we need to share the global resources. And also, and the difficulty is that for the OS to manage the allocation to the resources like optimally. So how can we like optimize this? And then difficulty locate the program error. As a result, they're not like deterministic and reproducible. So that's the difficulty we're doing. And here's just an example, like what's the race condition. That's the thing about it. So we just chain in and out. And then for echo, so we need to get the char, and then we need to base on input and output, and then just put char. Okay. So when, let's say the process one, we just invoke the echo and interrupt immediately after we call the get char. And then P2 invoke the echo, and then we just get a Y, and then P1 resume X overwrite, and then Y output it instead. So here's called a race condition, just like they're waiting for it, and then you didn't get the expected output or your original value. So we call the race condition. Okay, and for this, that's why we need to implement like also for the OS to prevent. Okay, when I execute in this way, okay, maybe in the beginning, how can I make sure if I try to read X, then I read the X. And then maybe I just like based on the CSCI get the input to the CSCI, then it's make sure it's to the out. And then when I put chassis out, then it should be one. And that's what we need to do. And for this one, how it's going to be like occur is called the race condition. Is like we have multiple processes or like the first like read and write data item. So that's what we need to make sure like read and write in a correct order. Okay. So the final result depends on the order of execution. Okay. So the loser of the race. So it's like in this case, is the process that update the last and we determine the final value of the variable. Okay. And for the operating system, when we design and manage the issue raised by the existence of a concurrence, so yes, I think the OS must be able to keep track of what was the process allocated and the allocated resource. Here's the thing: sometimes we need to, when we allocate, then we get it, and also remember to deallocate it. Also protect the data and physical resources of each process against the interface of other process. Just like we're using a flag, or like try to change it. So when I get the access, and then let other, if I have other process, it depends on the like the output of it, or I need to read the value, then just put a flag or Boolean to check. So make sure, okay, once it's ready and deallocate or release it, then they can read it. Okay. So ensure the process output the independence of the processing speed. Because you say, why is the different speed? We have same CPU or like process, but really because when we are multi-threading, and also we have like multi-thread, also we have multi CPU, so we never know the scheduler, like how they assign it. So maybe someday we assign like do it earlier, like in another core, and then that means that okay, then we maybe if you remember we have the trouble, it comes out, so we need to maybe put them to waiting, like adding to a queue, like once is for other, if we are like depends on others output, then we need to wait for it. Okay. So that's why I say, okay, try to make sure things like independent, that is okay. So for the process like integration, so we see that we have different degrees of the awareness, like awareness of each other's. We have a called a competition. So what's the problem as a result of one of the process independence of the action of others or time of it may be affected? So what's the potential? We have a mutual exclusion, deadlock, or starvation. So just like based on here, like different type, and then what's the possible potential error? So you need to kind of like have an idea. If I ask you, okay, if I have a competition relationship, then what's the possible like problem? Then how can we need to, what's the influence? Okay. Also, if a process like indirectly aware of like each other's, like let's say we share the object, so they are like cooperation by sharing, right? So they also have like mutual exclusion. They also have tag logs. Also the data coherence for this one. Also, yeah, same as the process depends on others' information, also the timing. And also the process like directly aware of each other's like this, then will be the same deadlock and starvation. And we talk about, you see the resource competition. So when they compete, it's like concurrent processes come into conflict where they are competing use of the same resources. Just need to know this definition. Maybe sometimes the I/O memory, processor time, like clock. We have three control problem right here, like mutual, and then maybe this enforces like two additional potential, but like deadlock and starvation. Here's an example of a code like when we have like like process 1, process 2, and then maybe, and you say we have a true. So proceeding and then enter the critical RA, and then we enter the critical section here. Follow up. So when we always have a true and then we checking condition. For the details, we can look at it. And which are the like requirements for the mutual. So it must be enforced is one thing, and then the process like will be stopped or like wait for it. Like must to do with the interference of others process. So make sure there's no deadlock, diversion, and the process must be not be denied access to a critical section. There's no other process using it, using, and then no assumption and make about the relative process speed or like numbers process. Lots of definition and how sometimes you need to know, but you don't have to memorize all this definition. Okay. And cooperating by showing that we need to like they are interact indirectly. For example, like through the sharing variables, we rewrite the buffers. So we talk about the read-write buffer. You need to know because for the all the IO or like sometimes the hard drive input, all this like we always that we call the driver. The driver is like is an interface helping us to handle it. And also when we reading, we have a buffer. Because let's say for the input, we are not like reading bit by bit, but we also like we have a buffer like reading a bunch of it and then to input. So let's say right here, here's an example, 2 items of data A and B. So they need to maintain the relationship like A equals to B. So A plus 1 equals to A, B plus 1, and then like 2 times B and A. And also here, like cooperation by direct communication, there's a message like passing, primitive, sending and receive message. Unlike, so they're not really like share it, but they just like send and receive it. So the mutual exclusion is not required, but deadlock and starvation can occur. So for this like condition, let's say for the direct communication, then you need to know, okay, what are the possible? So you need to know what's the mutual exclusion, or like what's the deadlock or like starvation going to happen. And if I have one concurrence, like let's say we have the cooperation. So we'll be right here. If we have the thread, the program, so they need to like work for all the interlifting and then the first instruction sequence. So they are cooperating together, this effects. So there are no like deterministic and then no non-reproducible. So they are really like hard to debug unless like carefully designed. So it's like just multiple. So, and then here's one of the example. You can look at it. I cannot read it. So another one is like let's say the space shuttle example you see right here. So we will like passing the data. Let's say the shuttle have 5 computers. So for one like primary the avionics and then system the pass right here. So 4 of them waiting together. So they can be like asynchronous. So asynchronous that means like they don't have they need to wait for it, like they maybe not like send it in the meanwhile instantly. So we need to waiting maybe have some time or delay for it. Okay. And then it can be like real time, like they can running all the control system and then also result like synchronize and compare like 440 times per second. So they keep comparing all the values like passing. And then the 5th computer is the backup fighting system. So called the BFS. So they stay synchronous in case it's need. So synchronize and make sure. So they can be like asynchronous. So working, they will update changing, but they will also like validate, like make sure they all have the same copy. But when you have a backup, just we have the backup, it's right here. If we have like 4, they're working together, they need to make sure the resources like data, maybe we have one variable. So they need to double check, okay, if let's say I have a B, C, D, E here. So if A is writing it, then I need to like let notice the others like, okay, everybody to read it. Okay, A update this value, I need to read it. and then we share everything. Okay, right now the new variable A is equals to 10, like this. So so it's synchronized. And then BFS need to back up, do the backup. So we need to make sure, okay, right now value variable A is equals to 10. So that one's will be this. And countdown abort because there's disagree with the past. So it's really have a chance. So it's like our synchronous cycles. So but due to a modification in initialization code of the past. So you just need to know, here's just an example. Also, we have the automatic operation. So we need to know what's the operating. So the concurrent program, so underlying automatic. So where's the, is the operation always running to completion or not at all? Okay. So it's the indivisible. It cannot be stopped in the middle, or stage cannot be modified by someone else in the middle. So it's called the atomic. Okay. Atomic operation. And a fundamental like building block. So if no atomic operation, then they have no way to affect to work together. So it's something is required. And on the most machine, like memory reference, like assignment, load, store, or word, like atomic. So when we load something, we cannot say when I load, I stop and let something. I have to let this loading instruction complete. I load A to certain register. When I store it, I need to like put the value like back to the main memory address. So this how can we guarantee, okay, nothing more. But some machine name like level language, they're the atomic, so they would double like precision floating point. So you can just need to know what we need. And also, what are the possible challenges? So we have like multi-threads like executing in parallel to share the resources. Also, we share the data. When we have like the fine grains sharing, so we increase the concurrency because we want to get a better performance, like concurrently, like multi-threading between, but it will make the more like complex. Kernel like grand sharing is simple to implement, but we have low performance, so it's a trade-off. So just like sharing a database and a row with a tables like this. Are we like sharing the row by row, or like share the whole table? Depends. Okay, if we share the row, like we can update immediately. But for the whole table, it's like whole, like as the idea. So if I concurrently, if I editing like every row of it in the database, so I can do like concurrently. So change it. But sometimes if you rely on it, then you can make sure that no deadlock or no mutual exclusion. If you just like copying and working as a table, is that like whole table, then you don't have a issue like certain one of item reading adding, then you just like replace the whole table. So it's more safe, but it's not efficient enough. Okay. Motivation. So the great thing about OS is that in the lots like between the problem of OS and problem in real life is just helping do this. We don't talk about real time. So you can think of, because here is the how it actually working on the OS system, because we have the clock this time. So it's a really similar like PA, the person AB, that means equals the process. So they do have their time periods like to execute to do some action based on OS. So let's say they look at it, look at our mail, leave the store, arrive the store, and then they look at the version of it, they will buy the mail, leave it. So you see, if they execute this one and then without checking each other's, then they will buy the milk twice. Okay, then how can we like prevent this type of error, and then you can like stop it? Let's say for two processes, you see the time period right here. So at 3:10, so person arrived the store, so it will check it, it will leave. Okay, but for person B, it will open the fridge, it's out of milk. Then how can we like prevent or avoid this problem happen? Let's say in reality, how can we avoid the problem? if they are not cannot communicate directly, yeah. So okay, you have. Okay, it's a note, but apply to the one we using like the example two. It's like before that, because right now it's like person B have a right to open it. Okay, it's pretty similar. Okay, if I note that means I need to read the notes, right? So I'm not going to open it. Or it's really much more crazy. After person A open it, check its alphabet, and then I don't like, because in this stage, like I know it's alphabet, nobody can access, right? I need to buy lock it. So it's a boolean, it's a fact, right? So it's same, I apply the same concept. So I lock it. So when person B come, it's locked. So I just wait. I wait until it open. That means I need to wait until person A come back, unlock it, like, or like I put the milk back, unlock it. Then okay, oh, check it. Okay, I have a milk, so I can grab it. Okay, so here's the idea, like the OS doing, or like how can we prevent it? Okay. Well, otherwise, like here's like we have a multiple, because like we write twice. It's the idea like for process I read it is empty, so I write a value. So and then process B read it is empty, right? So I'll take an action, I'll add it to. So it turns out result is like maybe final should be only one, but it turns out in this shape it becomes two. Okay. And when we talk about, it's more like synchronization. So it's we use the atomic like operation to ensure the cooperating between the threads. For now, like only load and store. So just need to know if I say what the atomic operation, load and store. That's it. And also show how to build like anything useful, only read and write. Okay. So also like critical section, we have like only like one thread to execute like at once, and then mutual execution, then we just like ensure only one thread executing a critical section. So one thread execute other there like while doing its task, and then the critical section mutual execution, like two ways describe the same things. Okay, and about the lock, just like prevent others from doing something. So here's the lock. So we hit the lock. So lock before enter a critical section, and then before access the shared data. So the shared data, the one is the fridge. So that one's the sharing is the milk. So unlock while like living, that means after accessing the shared data, that means I finish it, that I will unlock it. So let others do with it. So wait if lock. So here's the idea, stage. So I fix the milk problem by putting the lock on the fridge. So here's the one. And then like correctness of property, so need to care for the correctness of concurrent problem since they're not deterministic. So always write down the design behavior first. Okay, so and the impulse, I like to start the code first, and then when it doesn't work, put the hair out against that thing first, then code. Yes, of course, we do. But it's really hard to do that. And what's the correctness property? So never more than one person buy it and somebody buys if need. Okay. So just like applying in this logic when we are writing the program, since most of our application, or like when you are writing some assignment, working on some assignment for maybe for others, we don't have to really consider this part, because the OS it will help you to handle it. And also most of your program you're writing, like let's say you assign the C purpose, even you're simulating the OS doing, but from the view of the real OS or Linux system or the Windows system, it's just a piece of process. They have like execution time. Sometimes if you want to access the variables, they need to wait. So they will put it as like maybe have a wait, and then in the queue, and then maybe they will put it to the stack. So once like finish complete, so that's how it works. So right here, just a example. So just like, okay, so leave a note. This is what you say like before. So kind of a lock, and then we move the note after you buy it. It's possible, yeah, or like just don't buy it. So you can just like wait for it. Okay, here's the things. So even for the computer itself, okay, I will check the no milk, no note, then I will do it. was the action. Okay. So right here, okay, just like if I like too much milk or the occasionally, so no milk, no notes. If right here, no milk, no note. Leave the note by milk, remove note. So right here, so you can see the time difference right here. Still, if we execute in this part, it still maybe have a problem. Because when we checking, don't know what's the possible issue for this one. If I'm writing like the programs, it looks fine, right? Because I'm using the condition. But what's the problem for this one? Because like for the like concurrency, because like because like if you implement this program, it looks pretty nice, right? I check it. So I will check it. This is milk. If there's no milk, I will check. There's a note right here. I'll make sure if nobody going to buy it, right? So, but it's a problem maybe in another problem. It's like another process. We check it again. But when you check it, you still not yet put the note. Then how can we put it? So it's the same idea. So the first can like get the context switching after checking the mail and note, but before leaving a note. So how can we make sure we don't have a bug like this one? Or like if like this one, we can discuss like instead of looking solution, then how can we fix this one? Okay. Imagine that right now in our concept, because we just if you remember the example I gave you, we are kind of like same pieces. So I give you the same program, and then I have a call using a fork. So it's calling child. So every time you call, it's exactly same pieces of it, like exactly the code will be the same, everything is same. So when you do the check, another will do the check, but you just never know like which. Okay. Okay. That's what I mean. Maybe just allow one person to check it. Okay. So maybe I have a pen. Let's say I need to just like I need to grab the pen. Like I only leave the pen over there, just only one pen. Okay. So if I need to check it, do I have a meal first? Then I need to grab the pen first, right? Is it? Yes. So let's say if I say in this way, how do you think like if I say, okay, before I go into check, I have to grab the pen. I will put the pen over there. So I share, okay. Then who grab the pen first? Who can check all these things? If you cannot grab the pen, I will wait for it. And if you have pen, then you can write down the notes, right? So also like you check it, you can write the note. And then after I finish the note, then I put the pen back, or like I will bring the pen until when? Until I buy the milk and put it back and take out the note, and then I will put the pen back. So that means I finished everything. Then also I guarantee another process, like other person not allowed to write down any note. So they keep waiting to get it. So once the pen is over there, then I can go, I checking is the pen right here, is the pen right here, is the pen, wait, no. So once process A, the person A put the pen back. Okay, the pen is right here. So I grab the pen, I go to check the fridge. Okay, then I will see the milk is right here. Then I don't have any issue. So it's the idea that we can do it this way. So let's say here we fix it like the previous, we leave the note. It's like declare no meal, and I'll buy it, and then I will remove the note. So right here, so there's a human it's not really bad, but for a computer, no one ever buy the milk, right? For another solution, so leave a note A, and also we have like leave a note B. So I see, that's why I say we have exactly identical, like same they're identical, but like the code they're exactly same. We are doing exactly same instruction. Then we really need to think like when we are really executing this way, then okay, no note for B, like this one I have note B, right? Not it, then no milk, I will buy it. So I'll check like, do I have a note for me? No, then also this is no milk, then I will buy the milk. Okay, so if I finish, then we move the note. How about this one? So look at it. So let's say for flag I leave the note A, and I see maybe I will execute the B. So this one is the third way. For B, I will leave the note, and then I will execute note. Okay, just I leave the note. No, then okay, and then I see okay, if no milk, I will buy the milk. After I finish, did I have a note from B? Okay, no note. If yes, we have a note. How about this one? How about this one? Can you get what's the problem? It works now, it doesn't. Because I try to leave a note first, and then leave the notes. Could you understand what this one is doing?
So this one is there.
Mhm.
There's milk there.
First, thread A, we execute thread A first. We leave the note. Mhm.
Then and then B leaves it out.
Mhm.
So even that's regardless of whether there's any milk there or not.
Yeah, they still not yet check.
So, but if it is milk, that milk's gonna stay there.
Good.
Well, these and but you will-
Okay. Yeah, so then this way is like, I check, you have a note, and then you are not. So actually they won't, nobody will do. So it's really worse too. So that means like this approach is not available. So then we need to think about, okay, and then there's, so I'm not do that, you will do that, and then call that starvation. So that's, we call that situation. Okay. Maybe we have like two notes. So one is like, okay, different notes. So I'll keep checking. Okay, notes, do they have a note of B? Then was I do nothing? And then if your note B, do I have a note? So this one is like checking for another one. How about this one? How do you think? If you look at, how about this code? Everybody can help to explain this one. If you look at this one. So it kind of like same, right? Because we leave the note first, but for PA, we'll try to check like, is it there's a note over there? So I just wait, right? So this one is like guaranteed, make sure, like I would say, that means that B have higher priority to do that, take this action, and then A will wait for it. So if we go back to this sequence, if we leave a note, so both will execute, and then it's like trying to do it, and then we check. So not a note, but can we fix this one too? We just like helping others. They say, okay, so make sure somebody do it. But sometimes for this sequence, can we avoid the problem like this? If I put the values right here. Is it have the same problem? Yes, it's right. Because we're still checking. Okay. So that's why we need to still discuss. Like then we another one is the critical section. So here's why it's like because we always check no milk and buy the milk. And then solution 3 will but it's like unsatisfied shin. So we did like complex and also like even simple exception. So it's really hard to do that. So it's like BC waiting. So we always need to wait, and then maybe we don't know the actual orders. Maybe have a hardware provide better like high level primitive than the atomic low or store. So just thinking like this. So the abstraction of the text is good, like maintain the sequence execution model. Also, we allow simple like parallelism to overlap the IO computation. But unfortunately, so there's so complicated to do the SSS stage share within that. So this one. So mainly when we like implementing the concurrent problem, so we only taking care like loads and store. So it's really like tricky and error point. So it's always so we'll implement high level operation on top of atomic operation provided by hardware. So kind of like we call the synchronized toolbox. So it comes to here, and then we have one called a solution 4. Okay, suppose we software implementation like called the lock. So like wait until the lock is free and then grab it and then unlock it, like wake it up anyone for waiting. So they may be the atomic operation. So if two folks are waiting for the lock, so only one success to grab the lock. So here's like kind of just like go down to the final solution. That's like what I'm saying in the beginning. Just make sure that only one can do that. I have to check. So I just like I have a key or this one is the lock. So if I can go to check it. If yes, I buy it. After I finish everything, the task I did, then I'll release it. Just like I put it back. Just like I really put the feed instead of like I checking the notes, like who can even I keep like going back to check notes, but we still have an issue, then why not just keep just atomic issue? We'll get the only one key and then we do it. So here's we jump to it. So each one is called the critical section that's like within. And the last we will cover the one called like the mutual exclusion with the like hardware support. Okay. So right here, for the program, we have like the high level API, then we try to have a logs, and then we just like try to do all these steps, and then hardware mainly for atomic, we have a load and store. We try to disable or something like this. So we are going to implement that with high level, like synchronized like, primitive using atomic operation. So I think it's pretty painful, but only atomic primitive will load and store. So need to put primitive useful at the user level. So it's the whole idea of it. So we just like cover the last part of here is about the lock. It's like prevent someone from doing something. So lock before entering critical section and before accessing the shared data. Unlock when leaving. After accessing shared data. Wait if locked. So important. All the synchronized involve waiting. So should sleep for the long waiting time. So that's always sometimes we see like we have a log or like waiting or like just wait there until release. So that's what we need to do. Sometimes we call it awake or wake up. So let's say if we get the like only one access, then they are in the waiting stage. We don't know other program, maybe they are waiting in the queue and they will say, okay, all those queue we try to wake up, let them to gain the only one access. Okay. So maybe one of it like maybe P1 have it and then release it. Maybe P1 to P5 can compete for this one like only one lock. So once let's say P3 get it and then P2, P3, P4, we will like go back to sleep again or wait stage again. So until it release. So that's what we're doing. So we will doing like the interrupt disable and so the unit processing system, so we will disable all the interrupts, current mutual exclusion. But the design advantage is the efficiency of execution should be like noticeable degrade. Same idea because we're doing a multi-threading like or like multi-programming. multiprocessing, the purpose like doing like concurrently, right? So we can like execute like share like process by the multiple cores. So do it in same time, but when we also go back and we have to wait for each other, then just like fall back to the same idea, like unit processing system, slow. So it's not working for multiprocessor architecture. Then how can we do that? And then we need to modify it. But for the details, I will let you like we can start to work on the first next assignment and working the actual programming. Then you can understand more. Then you will know more about this detail. So I will cover in the coming lab. Also, I will based on the first one convert to C++ for the next step. So for the rest of it, then I will cover in the next lecture. So that's it for today's lecture. Thank you. Yeah. Thank you for listening.